Welcome to Speaker Night at the David Dunlap Observatory online with the Royal Astronomical Society of Canada, Toronto Centre. My name is Denise Chilton, and I am the RASC Toronto Centre DDO Committee Chair and an operator of the 74-inch telescope here at the David Dunlap Observatory. Together with our outreach coordinator, Quinton Wayrich, and our senior telescope operator, Chris Vaughn, I am delighted to be your host for tonight's lecture. I'm also very excited to welcome you, our viewers, to tonight's lecture. If you haven't already, please take a moment to say hi in the YouTube chat and tell us where you are joining us from. This helps us to make sure that all of our connections are working properly. The Royal Astronomical Society of Canada's mission is to enhance understanding of and inspire curiosity about the universe through public outreach, education, and support for astronomical research. In partnership with the City of Richmond Hill, RASC hosts outreach activities at the David Dunlap Observatory, or DDO. The DDO is home to Canada's largest optical telescope. While we miss welcoming visitors to the DDO facility, we are happy to bring you virtual programming like this instead. We would like to start by acknowledging that the David Dunlap Observatory in Richmond Hill stands on the traditional territories of the Wendat, the Haudenosaunee, and the Anishinaabe peoples, whose presence here continues to this day. We would also like to acknowledge this land is at the meeting place of two treaties, the lands of the Mississaugas of the Credit and those of the First Nations of the Williams Treaty. We thank them and other Indigenous peoples for sharing this land with us. It's my great pleasure to introduce our speaker for tonight's lecture, Dr. Nassim Bozorgnia. Dr. Bozorgnia is an assistant professor in the Department of Physics and Astronomy at York University. She obtained her PhD from the University of California, Los Angeles in 2012, and has held postdoctoral positions at the Max Planck Institute in Heidelberg, Grappa Institute at the University of Amsterdam, and the Institute for Particle Physics Phenomenology at Durham University. Her research is in the field of astroparticle physics and focused on the dark matter problem. More specifically, she's been developing various strategies to significantly improve our knowledge of the dark matter distribution in our galaxy with the aim of studying its prospects for dark matter searches. Tonight, Dr. Bozorgnia's lecture, Hidden in Plain Sight, the Elusive Dark Matter, describes what we currently know about this mysterious type of matter and how our current and future experiments and cosmological simulations will help unravel its secrets. If you have any questions for our speaker, please post them in the YouTube chat. Nassim will have time to take your questions at the end of her talk. Please join me now in welcoming Dr. Nassim Bozorgnia.
Thank you very much. It's a pleasure to be here, and I'm very excited to tell you more about the dark matter problem tonight. We have a lot of evidence for the existence of dark matter, but we haven't yet detected it. So in my opinion, it's really hidden in plain sight. And I'm going to talk about what it is and how we can search for it. So let's start by asking an important question. What is the universe made of? So everything that we can see or detect in one way or another makes our visible universe. So for example, atoms, which are in the periodic table and make up our bodies, trees, the planet Earth, our sun, and basically all the stars which exist in our Milky Way galaxy or any other galaxy. So whatever that you can detect in one way or another this all makes the ordinary matter component of the universe. But as you can see here in this pie chart, this is just 5% of the total matter energy budget of the universe. 27% is in the form of the mysterious dark matter, which we will talk about tonight. And 68% is in the form of something even more mysterious, dark energy, which is responsible for the accelerated expansion of the universe, but we even know less about compared to dark matters. And I'm not going to talk about this component, but I'm going to focus on the 27% dark matter component. And you might think, well, this is just 27%. Is it that important compared to the full matter energy budget of the universe? Well, if you focus only on the matter content of the universe, so this section of dark matter and ordinary matter, and if you calculate what percentage of this matter content is in the form of dark matter, you can find that 85% of the matter content of the universe is in the form of this mysterious and elusive dark matter, which we don't know much about, although we have a lot of evidence for its existence. And all the other matter, that is the ordinary matter, is just 15%. So we are basically here in this 15%. And the rest is just hidden, although I think it's hidden in plain sight. So let's think about when scientists thought about dark matter. So dark matter has actually a very long history. So already in the end of the, in the 1800s and the beginning of 1900s, scientists were thinking about this problem. So Lord Kelvin, which was a British physicist, estimated the mass of the galaxy already in the early 1900s using observed velocities of the stars. And he, at that time, found that there are some discrepancies with the mass of visible stars. So things did not match with the mass of visible stars. So he has a quote mentioning that many of our stars, perhaps a great majority of them, may be dark bodies, already in 1904. And then following up on the work of Kelvin, he had this theory of, kinetic theory of gases, was the French mathematician Poincaré, who followed up on this, and he was the person who used the term dark matter already in 1906. So again, scientists were starting to think about the discrepancies that existed in the masses in our galaxy, and that there is some hidden form of matter that we cannot see, and it does not interact with light. If we move on to the modern evidence for dark matter, this evidence comes from a variety of different observations and different scales, from the scale of dwarf galaxies, which are these small galaxies which are just going around, for example, a Milky Way-like galaxy, and these are just satellite galaxies bound to our galaxy, to the galaxies the size of our own Milky Way, and I'm going to talk about these evidences one by one, to clusters of galaxies, and up to the largest scale structures of the universe, and moving on even to the cosmic microwave background radiation. So we have, from all these variety of different scales, a lot of evidence for the existence of dark matter. So these can only be explained if we have this unseen matter distributed in the universe. So starting from one of the important evidences for dark matter, which is galaxy rotation curves. So in the 1970s, this is a work which was pioneered by Vera Rubin and collaborators, where they measured the rotational velocities of stars and gas around the center of galaxies like the Milky Way, and different sized galaxies actually. And they found that if you measure this rotational velocity as a function of a distance from the center of the galaxy, what you expect is that as you go to the outskirts of the galaxy, where you don't have too much stars or gas, the velocities should slow down, as you see in this curve. This is what is expected if all the mass of the galaxy is in the visible mass. But what they found instead was that as you go to the outskirts of the galaxy, the velocity actually increases and then reaches a plateau. And this was suggesting that there should be some mass in the outskirts of the galaxy that we cannot see. So this is a discrepancy from what is expected. So there should be more mass here in the galaxy. And since we are measuring the mass of the galaxy based on its visible components, this mass is not seen. And here is a little movie of how this, if it works. Let's try it one more time. So for some reason it's not working, but it basically shows that this one on the right is just, which is the actual, what we measure from the rotation curves of the galaxies, should be this galaxy, including dark matter, it is moving, rotating faster compared to this one, which we expected does not include dark matter and is just slowly rotating. So this is basically the same thing here shown in this animation, which unfortunately is not playing. So, now it is playing. So you see it here. So on the right, you see that this is just rotating faster compared to the one on the left, which would not include dark matter. So there should be some mass that we do not see, and it's causing these faster rotation of the stars and gas in the galaxy. So the picture that we had, this is just a sketch of a galaxy like the Milky Way, and this is a picture we knew of a galaxy. If you think about a galaxy, this is what comes into mind. And this is a picture we knew of a galaxy before the rotation curve measurements, before 1970s. We thought that galaxies should look like this. But after these measurements, we believe that galaxies like the Milky Way, if you zoom out on this, they are actually embedded in a very large sphere of dark matter, which is called a dark matter halo, which has a radius which is more than 10 times the radius of the visible galaxy. And you have a lot of dark matter here in the center, and then as you go to the outskirts, the density of dark matter just goes down. So this is the new picture that we have for galaxies, and we believe that the galaxies like our own are embedded in this large sphere of dark matter, or large dark matter halo. Now, this is still not the full picture, because if you could actually see all the dark matter in the galaxy, it wouldn't be in the form of this smooth, as you see here, shaded region that you have. This more black here is trying to just emphasize that there's more density of dark matter in the center. As you go out, it just becomes less. That's fine, that is there. All the evidence is showing that that's there, but there is also, if you could shine light on dark matter, if you could have seen dark matter, there is also a bunch of clumps of dark matter of different masses, and these are just rotating the center of the galaxy as well. So these are called dark matter subhalos, and there are hundreds of thousands of these of different mass subhalos, which are also in the galaxy. So this is also another component of the galaxy, if you could see it. So the picture of the galaxy has changed a lot from before we had all this evidence for the existence of dark matter. And another evidence comes from gravitational lensing. So what is gravitational lensing? If you have a massive body somewhere, it doesn't have to be dark matter, it could be any massive object. Einstein's general relativity tells us that this massive object would curve space-time around it. And so light, which is coming from some distant galaxy or some source of light in the distance, as it reaches to us, and if it passes this massive object, the light rays would actually bend. So basically, we have this is called gravitational lensing. Due to the gravity of this massive object, we have this effect. And what this means is that what we will see is not just one image of the distant galaxy, but we might see some distortion in that image. We might see some arc or a circle caused by this gravitational lensing. So how is this important for dark matter, and how is this an evidence for dark matter? Well, it doesn't matter if this is a luminous massive object or if it's a dark massive object. If you have some dark subhalos that I showed you, clumps of dark matter, you would have this effect too. So they still have the same gravitational effect on space-time, and then you will have this bend of the light. And this, we have a lot of this gravitational lensing observations, and you see one example here. So these arcs that you see here are these distortions that I mentioned due to the effect of some massive object between the light source and us. And we have a lot of these observations as well. So this is another important evidence for dark matter. Now, to tie into that evidence, and if you ask me what is the most compelling evidence for the existence of dark matter, maybe in one picture is the the bullet cluster, which is shown here. This is the collision of two galaxy clusters, and what you see here actually are two components colored in pink and blue. So the pink is the hot gas in the two clusters. So this is, again, an outcome of the collision of two galaxy clusters. And the hot gas is detected in X-ray. And because the gas interacts electromagnetically, it slows down. And so you see that this is the position of the gas here in this collision of the two galaxies. But then if you use gravitational lensing in the way that I just mentioned, you can pinpoint actually where most of the mass is for these clusters, colliding clusters. And they are not at the place where the visible mass or the hot gas of these clusters are. They are at a different position. And this is, again, determined via gravitational lensing. It's not directly observed, but we can figure out where most of the mass is. And this is just pinpointing that most of the mass is actually invisible. We cannot see most of the mass. And the reason that they are actually in a different position is that dark matter is believed not to interact. Well, it doesn't interact electromagnetically. So basically, it is not slowed by electromagnetic interactions. And so they actually pass each other first, and they end up somewhere else. Whereas these, the hot gas is slowed by the electromagnetic interaction, and so they are just at a collision. And we have, again, with the same color coding, where we have the hot gas in pink and most of the matter via gravitational lensing, we know that it's at a different location. It does not line up with where the gas is. And this is perfectly explained if we think that this is made of dark matter, which does not interact gravitationally. So another important evidence for dark matter actually comes from the cosmic microwave background radiation. And so what you're seeing here is really a snapshot or a picture of the baby universe. So when the universe was only 380,000 years old, this is the temperature fluctuations the different spots here are different temperatures. So hot regions and cold regions that you see from that point after the Big Bang, a picture of the universe. So why does this tell us about dark matter? So, and what is the cosmic microwave background radiation? So the CMB is really the oldest electromagnetic radiation in the universe. And the reason is that before this 380,000 years, passing after the Big Bang, before this, in the universe, we had these charged particles. And so photons, particles of light, would interact with these charged particles, so they could not travel freely. But after this point, neutral hydrogen atoms formed, and so the universe really became transparent to photons. So that's when the photons could travel freely to us, and this is what we see today, right? from that time. So these are the relic photons from the time that the universe became transparent to them. And they actually fill the entire universe today. And the background that they make is almost uniform, but you saw the fluctuations in this map. And these are really tiny fluctuations. They're just on the order of 1 part in 100,000 across the sky, very tiny fluctuations. And they have specific patterns. And their patterns actually tell us about the existence of dark matter. So if the universe did not include dark matter, you would not have this specific pattern in the CMB maps. And we have these maps to great precision. And so this is really very, to the percent level, we can tell from these cosmic microwave background maps the amount or the abundance of dark matter in the universe today. So this is really exciting and compelling evidence that we must have dark matter in the universe. Now, you can take this input that we have from cosmology, the amount of dark matter in the universe, the amount of ordinary matter, and you can actually simulate the universe starting from the time of Big Bang and include dark matter and see what happens to structures. And these simulations tell us that you need dark matter to form structures such as galaxies that we see today in the universe. And so I just wanted to show you a movie of one of these simulations. This is the Elusive simulation. And you see the time here on the bottom left. It's the time since the Big Bang. So, and what you're seeing is actually the density of dark matter here. And dark matter is just clumping under the force of gravity. So gravity pulls it together, and it basically forms these clumps as you see these regions here more dense. And you are basically forming this cosmic web of dark matter. Now, in a second, the movie will switch to ordinary matter or gas and show that how these would also fall into the gravity of these dark matter seeds. So here you see the ordinary matter, the colors are just the temperature of gas, and the ordinary matter just falls into the gravitational potential, or due to the gravitational pull of dark matter, it actually is attracted to that, and more matter is accreted, and it actually forms the galaxies or the galactic nuclei of the galaxies that we see, and some of them are really active. They have these supermassive black holes at its center, and they basically heat the matter around it, and so you have these bursts that you see here. And you see that this simulation stopped after 6 billion years. We know the age of the universe is much more than that. If you let it run until 13 billion years, then you would see that you form galaxies, like different types of galaxies, like our own galaxy as well as other types of galaxies. So if you take this cosmological simulation, run it until today, these are the sort of galaxies that you form in this simulation with the existence of dark matter. Now, these structures would not form if you run this simulation without dark matter. So you need dark matter to form these structures. And again, these look a lot like real galaxies, but they come out of simulation. So these are simulated galaxies. Okay, so we have all this evidence for dark matter. It is needed for structures to form, and again, compelling evidence across all scales. But we still don't know what is the nature of the dark matter particle, and all the evidence we have is just due to its gravitational effects, astrophysical evidence we have. If we want to consider, what is the actual nature of dark matter, we still don't know. So if we consider the standard model of particle physics, we have matter and we have interactions between the matter. So here you have the different types of matter, just the ordinary matter, quarks and leptons. And then you also have something called force carriers, which are in charge of the interactions between matter. So you have the photon, which is for electromagnetic interactions. You have the gluon for strong interactions. These are the nuclear interactions. You have the Z and W bosons, which are responsible for weak interactions like radioactive decays. And this all together is just the standard model of particle physics. But none of these particles actually can be the dark matter particle. We need to have a neutral particle. It doesn't interact with light, electromagnetism. We need it to be massive, and we need it also to be stable, not to decay so fast, because we have dark matter today in the universe. It shouldn't have all decayed away. So we have to go beyond this standard model of particle physics to think of some theory to explain, what can be dark matter actually. And there is actually a lot of different candidates for what dark matter can be. So this is a complicated graph, but it just shows the different candidates that can exist as dark matter. And you see some numbers here. So these are in some specific units that is used in particle physics called the electron volt for mass. And if you want to understand it a little bit better, the proton is here in these scales. So it's 10 to the 9 electron volts, which is also called giga electron volts, or GeV. But let's think about it in kilograms. This is a really tiny number. So the mass of the proton in kilograms is a 0, a decimal point, and then this is followed by 26 zeros and a 1. So this is a really, really tiny number, okay, for the mass of the proton. This is where it is. If you want to compare how small this is, compare it to the mass of a grain of sand, which is still very, very small in kilograms, but much larger than the mass of the proton, many less zeros after the decimal point here. Now, just to compare how light dark matter can be, it can be actually 10 to the minus 22 electron volts. But again, if you want to go to kilograms, this is a 0, and then the decimal point, and then this is followed with 57 zeros before the 1. So this is even a much tinier number. It's really, really hard to imagine these numbers, right? And the reason that particle physics physicists use electron volts instead of kilograms is basically because of these zeros. We want to avoid these zeros. But even in electron volts, this is very, very small. So this is a 1 divided by a 1 and 21 zeros following that one. This is how light dark matter can be. There's some theories for that. But it can also be quite heavy. It can be about 30 solar masses if it's not in the form of particle dark matter, but if it's the form of these massive objects, it can be the mass of the sun. So the mass of the sun in kilograms is a 1 followed by 30 zeros. So this is really huge compared to this number, to the mass of a proton. Of course, the mass of the sun is much larger than the mass of the proton. So this just gives you an idea of all the different candidates that we have for the dark matter. We still are in the dark about what the mass of dark matter is. And that makes it, in my opinion, very exciting that, we have a lot to search for to try to identify this elusive dark matter, what it is, the nature of it. So what I'm going to focus on in the rest of this talk is actually a specific region here in the mass of dark matter, which is about from the mass of the protons to 10,000 times the mass of the protons. And these are called WIMPs, or weakly interacting massive particles. And the reason I want to focus on this specific type of dark matter candidate is because it's just one of the most extensively studied class of dark matter candidates. So weakly interacting massive particles are, beyond the standard model of particle physics. They have been studied a lot, and the reason that they are rather exciting and were for a very long time is that if you consider dark matter particles interacting, they can produce the standard model ordinary particles that I talked about. They can produce that. And here you're seeing the annihilation of 2 dark matter particles going into 2 standard model particles. And if the dark matter particles actually interact via the weak interactions, then you would actually get the correct abundance of dark matter that we see in the universe from cosmological observations and the evidence, as I mentioned, if they interact via the weak interactions, this is you get the correct abundance today. And their mass should be between 1 to 10,000 times the proton's mass. And a benefit or a bonus that we get for these types of dark matter particles is that we can experimentally search for them. And there is actually a huge worldwide program to search for these kind of dark matter particles. So we have 3 complementary ways to search for WIMPs. These are called indirect detection, direct detection, and collider searches. I'm going to spend a little bit of time introducing these different methods and what we need actually to find dark matter in this way. So indirect detection, the same graph that I was showing, we have 2 dark matter particles annihilating and producing standard model particles. We cannot directly see the 2 dark matter particles which are annihilating, but we can, of course, see the standard model particles that are the product of this annihilation. And you can search for these. And one of the interesting outcomes are gamma rays that you would have here. And so you can have space-based telescopes or ground-based telescopes which can search for these gamma rays, which are the product of the dark matter annihilations in our galaxy. Now, if you want to see how this gamma ray products would look like, you can again try to go to simulations and simulate this. So what you would expect the gamma ray flux from dark matter annihilation in our galaxy to look like is something like this. So I mentioned the density of dark matter at the center is larger, and then it just becomes less and less as you go to the outskirts. So you have more dark matter particles annihilating in the galactic center, so you get this flux of gamma rays from dark matter annihilation, and then you have less at the outskirts of the galaxy, if you can think of this as a sky map of the galaxy. You also have some substructures or the clumps of dark matter I mentioned, and some of them you might have also these gamma rays from them as well. So you see this here in this simulation as well. Now, this is what you expect. Again, this is just from a simulation, but you have to also consider all the astrophysical backgrounds that we have for gamma rays. And this is a huge background. So this is the sky map by the Fermi the Fermi satellite, space satellite, and you basically see the gamma rays from the disk of the Milky Way, and then all these point sources here, which can be multiple things. It can be active galactic nuclei or pulsars, but these are all astrophysical sources which produce gamma rays. So if you're looking for a signal from dark matter annihilation producing gamma rays against very huge background, astrophysical backgrounds from sources that we know produce gamma rays. So, from just astrophysical sources. So this is a very, very difficult problem. And there are, a lot of advanced ways to search for these and subtract this gamma ray background. And a lot of people are working on in this field. It's a very active field of research, looking for signals from the center of the galaxy and from elsewhere as well. So this is very exciting. It's an indirect detection of dark matter. The other way you can search for dark matter is actually producing dark matter in colliders. So you can have 2 standard model particles coming together, colliding, and then you produce dark matter particles. So the same sketch I showed you, but going the other way. Instead of the dark matter going to standard model particles, you have standard model particles going to dark matter particles. And here, I'm just showing you an image of the Large Hadron Collider, which is this large collider. It's 27 kilometers in circumference between France and Switzerland. And you see it here. It's underground. And what happens here is that you have 2 proton beams colliding together and producing a bunch of particles, and you want to search for dark matter there. So this is an animation of what is happening in the LHC. You are boosting these 2 proton beams. So these are all the boosters that boost these to really high speeds, about the speed of light. And they are going in opposite directions. and now they're entering the large colliders. And you have these 4 detectors, actually, that you can try to detect what happens there. So this is a tunnel. It's showing you the tunnel, and then the proton beam is going in this tunnel under the ground. These are the 3 quarks in a proton. And this is just traveling, and it goes to one of these detectors, and it comes together with another proton beam. It collides. You see the other one coming from the other direction. They collide, and then they produce all these different particles that we expect them to produce. These are really high energies and really high speeds, and they produce these particles. So what about dark matter here? They're going to produce a bunch of particles that we expect this collision to produce. You don't see the dark matter here. The dark matter is interacting very weakly, just scatters away out of the detector. What you can actually measure precisely is you can figure out if there is some missing energy here. So the dark matter, if the dark matter is produced in this way, it will go out of the detector, but it has some energy, right? So you will have some missing energy in the total energy that you will have from this collision. And based on that missing energy, if you can pinpoint exactly how much energy goes in which particle, you can figure out indirectly, basically, that you have produced dark matter. So it's, again, a very difficult study, but one of the goals of the Large Hadron Collider is to search for dark matter in this way. Finally, the other method to search for dark matter is direct detection. And in my opinion, this is maybe well, not the easiest, but one of the more important ways to search for dark matter, because you can directly try to infer the existence of dark matter by searching for the dark matter colliding with the usual ordinary matter or standard model particle in an underground detector. So the dark matter comes in, it collides with a particle in your detector. The dark matter, again, will scatter away. So again, it's called direct detection, but you're not directly seeing the dark matter, but you're directly seeing its effect on the ordinary matter in your detector. So what is happening here, to go in a little bit more detail, we expect that we are sitting in this dark matter halo, right? And the sun is actually moving throughout this halo, and the Earth is moving around the sun. So we are expecting that we have a lot of dark matter particles actually passing through the Earth as the Earth is going around the sun going around the center of the galaxy. So basically, billions of these WIMPs should be passing through the Earth every second. But as I mentioned, they're very weakly interacting, so they don't interact that much. And what happens is that a dark matter particle would come into your detector. You have some ordinary matter particle in your detector. This is some nucleus in the detector, depending on what the detector is made of. The dark matter goes away, but it will actually collide with this nucleus, and it might cause this nucleus to recoil. So there would be some signal due to this effect, and there is going to be some transfer of energy to this nucleus. And what these direct detection experiments do, they measure, or they aim to measure, this tiny recoil energy after the collision of the dark matter particle with the nucleus in the detector. And these are, again, because the dark matter is very rarely interacting, these are rare events, and you expect only one event happening in a kilogram of detector material when you run the detector for 1 year, and actually much less than that. So that's why these detectors are now going larger and larger. They're reaching ton scales, and they have to run for multiple years to see even one event. And dark matter, of course, has not been detected yet in this way. So there's a big effort to detect it. Now, they are underground. They have to go underground. And the reason is that you have a lot of background. And these are from cosmic rays or environmental radioactivity. And they can mimic the dark matter signal. You want to get rid of those backgrounds. So a lot of these detectors are up to several thousand meters below the Earth's surface. So, and they are operating there to get rid of all these backgrounds that you would have. there is really a large global effort in the direct action experiments trying to search for dark matter. And you may notice here that we have SNO Lab. So SNO Lab is Canada's deepest underground laboratory in Ontario. And we have some new experiments, especially Super CDMS coming online soon in SNO Lab. So these are really exciting times. These are the new experiments searching for dark matter. And you see this whole worldwide effort across the world searching for dark matter in this way. Now, if you do have a positive signal at some point, this is what we hope, that one of these experiments would really detect dark matter. In that way, you can specify the dark matter mass and its interaction strength. So it can tell you, where the dark matter mass lies, what is its interaction strength more specifically. But in order to do this calculation, you need to know how much dark matter in the first place you have, right? So how much dark matter there is around us. And also you need to know how fast the dark matter particles are moving around us. If you don't have that information, you can't really figure this out, the mass and the interaction strength of dark matter. So you can't figure out what the particle nature of dark matter is if you don't have this information about the distribution of dark matter around us. So that's why it's very important to try to map the dark matter distribution around us. And this is, again, a difficult task, but indeed an exciting one. It's like finding a needle in a haystack in reality, because you have very tiny interaction rates, you have large backgrounds, and we have uncertainties in the dark matter distribution around us. And I want to talk a little bit more about this, about the dark matter distribution around us. So what is the dark matter distribution if you want to consider some region around the sun? So if you imagine this is the Milky Way and this is the sun, and if you consider some region around the sun, because these experiments are underground the Earth, so we need to know what is the distribution of dark matter, not throughout the galaxy necessarily, but just around us. And we can ask this question, what do we know about this? So you can have a theoretical model to explain it, and this is the simplest model for understanding the dark matter distribution. And this is what I mentioned at the beginning, that we expect that we have a spherical halo of dark matter particles in the galaxies. The density of dark matter is the largest in the center of the galaxy, so a lot of dark matter here in the center. And then as we go to the outskirts of the galaxy, this just decreases, right? And if this is the density of dark matter as a function of the distance from the center of the galaxy, it decreases as 1 over the distance squared. Now, the dark matter in the solar system itself, is the density of it is very low. So if you remember, we mentioned that the mass of the proton is 1 giga-electron volts, and the dark matter density in these particle physics units is 0.3 giga-electron volts per centimeter cube. So to understand this a little bit better, make the connection to everyday life maybe, this just means 1 proton mass in 3 centimeter cube. And if you want to write it in grams per centimeter cube, this is, again, a very tiny number. So it's a 0 decimal point and then 24 zeros and a 5. So this is a very tiny numbers in grams per centimeter cube. But just to understand it again in a little bit in real life terms, this is saying that there is 1 dark matter particle per your coffee mug. Okay, so if you consider just an average size coffee mug. So in the solar system itself, the dark matter density is low. And if you consider just the combined mass of dark matter in the solar system, if you put it all together, you're going to get the mass of an average asteroid. So this is tiny. So it's really a small amount of mass in the solar system. Now, how do we measure this? So I mentioned this is basically comes from a theoretical model, but you can actually measure this. And we have, again, a long history of the measurements of the local dark matter density. And the way to measure it is by measuring the vertical velocity of the stars which are near the sun. And from there, you can figure out what is the gravitational pull that is exerted from all the mass that there is in the galaxy, and you can infer the mass that is in the dark matter in that way by knowing what is the luminous matter's mass. And again, it's a complicated way, but it's we have some historical measurements for dark matter which are actually not too far off from the recent measurements for the dark matter density. So another way to make these measurements is to model, so theoretically model the mass of the Milky Way, both the luminous mass and the dark matter mass, and then fit this to fit the models that we have to these observations of the rotation curves that we have for the Milky Way throughout the Milky Way. So this is another way to cross-check the density of dark matter in the galaxy and it in our local position. So we have some historic measurements, as I mentioned, for this. So already in the early 1900s, the Dutch astronomer Kapteyn used these measurements of the vertical velocities of the stars to calculate the density of dark matter around the sun. And his measurement, which is, you see this number, is not too far off from recent measurements. So now we have a bunch of different observations for this. And the recent measurements for the local dark matter density, this was a little bit lower, but we have some uncertainties in this. So it can range between 0.3 to 0.6 giga-electron volts per centimeter cube. So we have some measurements for this. Is again a very tiny number, but we have measurements for the local dark matter density using this method. The other thing which we have to do for understanding the dark matter and how it's, the way that it behaves in our galaxy is to see how fast the dark matter particles are moving around the position of the sun. Okay, so this is quite tricky because we can't directly measure the velocities of the dark matter particles. But what we can do is go to one of those simulations that I showed you the movie for. Go to a galaxy which looks like the Milky Way, and in the simulation you have all the dark matter particles, right? So you can find the dark matter velocities in that way. And this becomes important again for understanding the dark matter, what the dark matter experiments would observe. So try to interpret the results of this. You need to know how fast the dark matter particles are moving to your detector. And so this is showing you one of these simulations. So you're seeing the visible matter here. And if you zoom in into one of these regions, these are cosmological large volume simulations, but you need to zoom in a lot to actually see a galaxy the size of our Milky Way here. And this is one of these galaxies. These are all simulated galaxies. So this is an edge-on and a face-on image of the same galaxy. And these were a little bit older, now old, because this field is growing very rapidly. But now we have even better simulations with more particles. So these simulations need many hours to run on supercomputers. You cannot run it on your personal laptop. You need supercomputers to run them. You simulate the universe again from the Big Bang until today, and you end up with these galaxies which look a lot like the Milky Way. So you can look at criteria, some criterias to match these galaxies with the Milky Way and find one which looks a lot like the Milky Way. And then you can go to one of these simulations and figure out what is the dark matter velocities in the solar neighborhood. And the way that this is done is to consider some region in the simulation which is around the solar circle where the sun is supposed to be, and then figure out the velocities of the dark matter particles there. And what we find by doing that is actually we get numbers, right, for these velocities. They have a range of speeds, but most of them have to be moving and actually are moving around 220 kilometers per second in different directions. And this is similar to the speed of the sun around the center of the galaxy. But the sun is moving in one specific direction, rotating around the center of the galaxy. Dark matter particles are just moving in random directions. So we can use all of this information from simulations to then go back to the experiments, and if they have some positive signal, to try to understand those signal, we can plug in these numbers, the information we have for the dark matter distribution to understand the results of those experiments. Now, in the last parts of the talk, I want to mention a different way to search for dark matter, which is quite an exciting new way for searching for, again, these elusive particles. So we have this map of the Milky Way now. This is the Gaia space satellite, the European satellite, which measured the position and velocities of more than 1 billion stars in our galaxy. And we have this really revolutionary map of the Milky Way now. This is very exciting times because this is all the, we have all the stellar information here, and we can use this to get information about dark matter. So how do we do that? So what Gaia has observed is a bunch of stellar structures in the Milky Way. So what are these? These are called stellar streams. And they form when you have some dwarf galaxy, for example, falling into the gravity of a bigger galaxy like the Milky Way. Because of the gravitational pull of this host galaxy, the stars in this dwarf galaxy will be perturbed, and they're going to actually form these elongated structures, which are called streams. It looks like some stream of water, if you want, around the center of the galaxy. And we have multiple of these stellar streams obtained, detected now with Gaia. They have each their own name. And how does that relate to dark matter? So if you remember, I mentioned that this is the picture of the galaxy that we have, just the visible part of the galaxy. But in reality, this is embedded in the halo of dark matter. And we also have a bunch of clumps of dark matter. If you could have seen these dark matter clumps, you have all these clumps of dark matter here too. So this, the disk of the galaxy, the visible parts, all these stellar streams are embedded in this halo and subhalos of dark matter. So what does that mean for dark matter? You basically can have these subhalos are moving around the center of the galaxy. They could go through these narrow stellar streams, and they can perturb these streams. So they can cause some effects on the stars, the positions of the stars in these streams. And these are detectable in Gaia and future astronomical surveys. And what I mean by this is the following. So if you take, for example, one of these streams, this is the GD1 stream, which is a very long and narrow stellar stream. If you zoom in onto it, this is the actual data of this stream, and these are some positions over the sky. You basically see that this stream is not just, the density of the stars in this stream is not uniform. You have some gaps and some features here in the stream. And if you actually simulate a dark matter subhalo going close to the stream or going through the stream, this is a simulation of this stream, you see that you can actually make the same perturbations of the observed stream. So this is quite exciting. And this is a very new way, an exciting way of detecting the existence of these dark matter clumps or subhalos in our galaxy. So it's a completely different way than the 3 different methods I mentioned before. But again, it helps us map the dark matter distribution in our galaxy. And it's very exciting now with all the astronomical data that is available to us. So just to conclude, if you think about what we're doing here, it has some similarities to what some of the ancient explorers were trying to do when they were trying to map the world. So this is actually an image of the map of the world in 1560 from the Library and Archives Canada. And what these explorers did was to just go to some unknown territories and try to understand, not knowing actually where they're going to go and what they're going to find. But they made discoveries, and they found different pieces, piece by piece, and put everything together, making this puzzle complete. And this is similar to what we are trying to do. We're trying to really map the dark matter distribution and use this map to identify the nature of the dark matter particle. So to summarize, we have a lot of evidence for the existence of dark matter from many different types of observations, but we still have not detected dark matter itself. So we don't know what the nature of dark matter is. There is really a worldwide theoretical and experimental effort which is underway to unravel the nature of dark matter. And I mentioned cosmological simulations, observations, astronomical observations that we have, and also many different types of dark matter searches. And they're going to all come together to tell us more about the secrets of dark matter. And it's really an exciting time, I think, because the next generations of the experiments, the upcoming observations that we have, and also the simulations that are becoming better and better with all the progress that we have in the numerical methods and the computational methods, this can be really helping us to unravel the dark matter mystery. And I just wanted to finish with this poem by a famous Persian poet and astronomer and mathematician, Omar Khayyam, which says, "For in and out, above, about, below, is nothing but a magic shadow show, played in a box whose candle is the sun, round which we phantom figures come and go." Thank you very much.
Thank you so much, Dr. Bozorgnia, for sharing this amazing research into dark matter. We are going to check in now with our RASC DDO outreach coordinator, Quentin Wayrich, who has been monitoring the YouTube chat for questions from our viewers. Quentin?
Thank you so much, Dr. Bozorgnia. I wanted to once again ask if anybody in the chat has any questions, please feel free to ask them. I am still monitoring the chat and I will be sure to pass them on. But in the meantime, I have a couple questions of my own that I'd really like answered if you'd be willing.
Yes, for sure.
Thank you. My first question is, why is it that the dark matter halo around the Milky Way appears spherical in shape rather than disk-like, like the galaxy itself?
It's a very good question. So the reason that we have the disk-like luminous disk of the galaxy basically is that the gas in the galaxy actually interacts electromagnetically, so it loses energy and it obtains angular momentum and it falls into the shape of the disk. Whereas dark matter does not lose energy in that way, so it does not form these disk-like or compact objects. It's just more a diffuse form of structure, so that's why the density is also not so high. It's just gravitationally bound. It's not electromagnetically interacting, so it's just the gravitationally bound object, and this is the form that it will make due to the effects of the gravity.
I see. Okay, that makes a lot of sense. I also wanted to ask, when I was younger, I read about a possible dark matter candidate called a massive compact halo object, or a MACHO.
Mm-hmm.
Are these objects still being considered as dark matter candidates, and what are they?
That's a very good question. So originally, many years ago, as you may have remembered, these came, the theories of these machos were considered at the beginning, and at that time, they were thinking maybe these are just the ordinary matters, but we cannot see them. But if you consider all the ordinary matter that might not be seen, like, for example, brown dwarfs or even some planets that might not be visible to us, they cannot make up all the mass of the dark matter that you see. So they're just a tiny fraction of it, so they cannot be that. But currently, actually, one of the candidates for dark matter are these primordial black holes. So if I go back to one of the slides there, this is one of the candidates of dark matter. These are black holes which formed, so you see these massive objects. These are, can be many solar masses actually. And these have formed in the first few seconds after the Big Bang. So they're not astrophysical black holes, but they are different types of black holes which can be compact, they're compact and they can be as type of dark matter. And you can think of other theoretical candidates which are compact but non-ordinary type of matter, they are compact objects and they are dark matter. So they are still considered in some specific theories, and they have to have specific interactions for them. as well.
Okay, thank you.
Sure.
We actually have a question from the chat now from a user going by AB, who asks, well, first of all, thank you for the awesome talk. Are there any other explanations for perturbing stellar streams within the Milky Way besides a dark matter subhalo? For instance, a wandering black hole or a close encounter with a globular cluster?
Very good question. Yes, so one has to be careful in that study as well, because you can consider there might be some, astrophysical objects which are passing by. So a black hole would have a very different structure compared to the dark matter. So if you consider the dark matter, again, as this diffuse ball of matter, they are usually much larger than a compact and tiny black hole. So black holes would not make the same effect on the streams. But you can think about, as you mentioned, globular clusters or something else, coming by and making these effects, similar effects. So one has to be careful in these computations. Now, the GD1 stream that I showed you the picture of, this is one of the streams which is really preferred stream to look at because it's actually quite far from the disk of the galaxy where a lot of things are happening, a lot of astrophysical things are happening, and it's rather far from the center as well, and it's also a very old stream and it's very long, and so the effects that you might see is usually considered not produced by just the ordinary matter, astrophysical type of matter that you might have. So this is one interesting candidate, but of course you have to be careful that you are not including, considering something which might be due to something else which we know of.
Right. I actually had another question about the Gaia image that you were just showing. There were a lot of stellar streams in that image falling through the Milky Way. So how many dwarf galaxies are orbiting the Milky Way? Is it more than just the Large and Small Magellanic Cloud?
So it's not only the dwarf galaxies. It's also globular clusters, which can be, perturbed. And a lot of these streams are actually made by the globular clusters, which are falling into the gravitational potential of the galaxy and forming these streams. In terms of the dwarf galaxies, the Large and Small Magellanic Clouds are two examples, but we have multiple others as well. But these are still, just the satellites, they haven't formed into streams. These streams, some of them are really old, dwarf galaxies or globular clusters, many giga-years ago, which came into the galaxy, and they were perturbed in this way by the gravity of the galaxy, and they form these streams. So, for example, GD1 is really an old stream. So this happened, many giga-years ago.
I see. Okay, so a lot of these streams could have been formed by dwarf galaxies, which have now ceased to exist.
Okay. Exactly. Yes.
Okay. I also wanted to ask. We spent a good portion of time talking about WIMPs. Would it still be possible to determine what dark matter is, like what mass class it belongs to, if it doesn't interact through the weak force?
Yes, so there are other experiments that I didn't go into all that detail due to time, but if you consider other types of dark matter. So for example, let me just go back to the stellar stream. So if you consider the stellar stream interaction with dark matter subhalos, dark matter does not have to be in the form of WIMPs. As long as you have these clumps of dark matter, they could be different types of dark matter. It could be self-interacting dark matter or other types of dark matter making these clumps of subhalos of dark matter. They could still interact with the streams and will have a signal. And is actually using the streams is actually a very interesting way to figure out the nature of dark matter too. Because, for example, if dark matter has a different types of interactions, you expect it to have a different distribution in the mass of the subhalos and also the internal structures of the subhalos. And so by looking at the details of the interaction of the subhalo with the stream, you can figure out basically this is a light into the nature of dark matter too. So, for example, I talked about mainly collisionless dark matter, but you can think of other types of dark matter and get an idea about the mass of dark matter using streams, and that's also a very exciting method to use as well.
That's fascinating. Thank you. The only thing I wanted to ask, the only other thing I wanted to ask is what first got you interested in astronomy?
Yeah, that's a great question. So when I was in high school, there was a stargazing event that I participated in, and that's the first time that I really felt, we don't know a lot, and there's a lot to learn by looking at the stars. Just the vastness of the universe and all the mysteries that it holds. It really inspired me to think that I want to pursue this further. And that remained with me. And, I chose physics and astronomy when I did my studies. And, when you start your studies in undergraduate, your undergraduate studies, you learn a lot of interesting things and all the interesting research you hear from everyone else. And you see that the field is vast and it's just so many exciting possibilities for research. So that's where I, continued.
It really is a vast field. There's so much, there are so many cool topics to learn about in astronomy. Yeah. Well, thank you very much for talking with us tonight. I believe that concludes the question period.
Sure, you're welcome. Thanks for having me here.
Thank you so much, Quentin, for relaying those great questions. And thank you so much, Dr. Bozorgnia, for answering them in detail. We have learned a lot tonight. We do still have a little bit more on our program for you this evening. It would not be a DDO online event without a tour of the DDO. And of course, you can see that I'm sitting here in the dark. We do have some live views from the scope coming up, so stay tuned for those. But let's get started with a short video tour for you to talk about the big telescope and a little bit about its history. Hello and welcome to the David Dunlap Observatory. Behind me is Canada's largest optical telescope. My name is Denise Chilton and I am a rascal, a member of the Royal Astronomical Society of Canada, Toronto Centre. It is my pleasure to be an operator for this telescope, and tonight I'm going to give you an inside look at this telescope and how it works. But first, let's think about the history of this scope. This facility opened in 1935. Originally, it was a research telescope for the University of Toronto. It was named in memory of David Dunlap, who had thought that he was going to provide some funding for the construction of this scope, but his unfortunate death prior to that funding being secured put the future of the scope in jeopardy. It's very lucky that his widow, Jessie Dunlap, came forward to donate the funds for this facility. The telescope was built by Grubb Parsons in England, in Newcastle on Tyne, in 1932 and 1933. It was shipped across the Atlantic in pieces after being completely built and assembled and then disassembled in England. It was shipped here and rebuilt on this site, and it opened in 1935. It was in use as a research telescope for many years, but unfortunately, due to light pollution and the availability of bigger and better research telescope facilities, the University of Toronto closed this telescope in 2008, and the property was eventually sold to the city of Richmond Hill. The good news is that the telescope is now open for public tours. Unfortunately, with COVID, we can't have people in the building, but tonight it will be my pleasure to show you how this telescope works. So how does a telescope work? Well, a telescope points outside at the night sky. Light flows down the optical tube, light from moon or stars or planets or dark sky objects, and it's collected by the great big mirror behind me. This is the primary mirror in the telescope. In this case, this one is 74 inches across, or 1.88 meters. You can probably see my reflection back there behind me, and it's this diameter that makes this telescope so powerful at collecting light and at being able to see very distant objects. When this facility opened in 1935, this became Canada's largest optical telescope, taking that record from the Dominion Astrophysical Observatory in Victoria, British Columbia. Their mirror is only 72 inches in diameter. Rumor has it that when Dr. Clarence Chant, who commissioned this telescope, placed the order for this mirror, he asked specifically for it to be 2 inches bigger than the Dominion Astrophysical Observatory's telescope mirror, so that he could have the record of the largest telescope in Canada. When this opened, it was also the second largest telescope in the world. No longer the case, of course, as much larger optical telescopes have been created since then. To get back to how a telescope works, light flows in from the night sky outside and is collected by this great big primary mirror and bounces back in that direction toward you. I'm not sure if you can see this contraption at the top end of the telescope here. This is the secondary mirror attached to these vanes. The secondary mirror collects the light from this primary mirror and sends it back down the telescope to the hole in the very center of the mirror. This hole leads to an eyepiece down below, and that's where you, if you were here, could come and look through the telescope and see distant planets, distant stars, or dark sky objects. You might have noticed that the sun rises in the east and sets in the west. If you were to stay up all night, you might notice that all of the objects in the night sky do the same. The moon, the stars, the planets, and more. This is because the Earth is rotating. But what this means is that the telescope needs to be able to lock on to night sky objects and then track them across the sky as the Earth rotates. So we have some controls over here that allow us to lock onto our targets. Every object in the night sky has a set of coordinates. We call these coordinates right ascension for east to west and declination for north to south. These are the same as latitude and longitude coordinates for objects on Earth. Let me show you how our controllers work. This is our declination controller. It helps the telescope move north to south. Let's watch how that works. As the telescope is moving north, we can see the coordinates in the counterweight on the other side of the telescope, so we know exactly where it's pointed. Now that we have our declination coordinates locked in, north to south, we're going to lock in our right ascension coordinates, east to west. We use this wheel to do that. First, we unlock the telescope. And then we can turn the wheel, and our coordinate system is up here on the setting circle so that you can see where the telescope is pointing exactly. And we turn the wheel until it's pointing in the right direction. Once the telescope is pointed in the correct direction, we need to lock it in place again so that it doesn't swing around. But you might have noticed that the telescope is no longer pointing at the open sky. Instead, it's pointing at the inside of the dome. So we need to rotate the dome roof to bring the open window in front of the end of the telescope. The dome weighs 80 tons. It rotates on a set of 24 train wheels connected to a cable and pulley system powered by a motor downstairs. Once the open shutters are in position, we're ready to start observing the night sky. Just up this ladder, we can find our way to the eyepiece. I wonder what I'll see tonight. Thanks for joining us for this virtual tour of the David Dunlap Observatory. We hope to see you here in person as soon as we're able to reopen the facility for public tours. Until then, wishing you clear skies. All right, I hope that tour of the DDO got you very excited about potentially visiting this facility coming up in the next few months, we hope. And we have tonight for you a very special view live from the 74-inch telescope. We have Chris down on the observing floor. Chris Vaughn is our senior telescope operator here at the DDO for RASC. Let's go down to Chris for a live view now from the 74-inch telescope. Over to you, Chris.
Thank you, Denise. Hi, everyone. So I've been sitting here enjoying the view of the bright star Regulus dancing in the camera through our 74-inch telescope. So Regulus is the brightest star in the constellation of Leo the Lion. And once our program's done this evening, you can head outside if your skies are clear. Look to the southwest, and about halfway up the sky, you'll see a brilliant blue-white star shining, kind of dominating the scene, and that's Regulus. And if you look carefully above it, you'll be able to trace out a pattern of a backwards question mark made of another 5 or so stars, a little bit fainter than Regulus. So Regulus, as I said, is the brightest star in the constellation of Leo. If you put binoculars on it, you may notice a small star sitting off to the kind of right-hand side of it a little bit, and a telescope view of the star will actually split it into a tiny companion. It's actually a multi-star system. Now, we can't resolve the pinpoints of a star through even the biggest telescope here at DDO, but the bloated image that you're seeing here, this dancing image that you're seeing here, is actually the effect of looking at that star through about 100 kilometers of Earth's atmosphere over our heads in Richmond Hill. Combined with that is we've got a little bit of overexposure happening in the camera because the DDO telescope collects so much starlight through it. And as you watch, you can see the image fluctuate. Those are the different pockets of turbulence in the atmosphere between us and that star's light. You might notice that the star is a little bit of a white or bluish white color. That's because this star is actually a much hotter star than our sun. It has a temperature of about 12,000 Kelvin on its photosphere, which is about double our more golden yellow sun. And it sits about 78 light years away. So we're seeing light that's taken 78 years to get here. Now, that means that this star is relatively in our neighborhood. It's kind of a neighborhood star of ours, or a next door neighbor, if you like. And that's allowed us, some of our biggest telescopes, to view the star's characteristics in a bit more detail. So whereas the star might look very simple at first appearance, it's got some really interesting secrets. So for example, spectroscopy has revealed that there's a tiny white dwarf star orbiting this star Regulus every 40 days or so, and it's actually underweight. And what astronomers think happened is that the gravity of Regulus drew or pulled off matter off the white dwarf star and reduced its mass and built up Regulus's own mass. And as a result, Regulus has begun to spin faster than normal. Our sun spins about once every month, rotates on its axis about once a month. This star Regulus spins on its axis once every 17 hours, incredibly fast. And because of that, it's got an oblate shape. So it's squat in the north-south direction, and it's got a wider sort of equatorial region, almost like a pot belly, if you want to think of it that way. So next time you head out, take a look at Regulus, find the star, very easy to see, and just think about some of these interesting aspects. And if anybody has any questions, I can entertain some questions too.
Thank you so much, Chris, for this incredible view of Regulus from the David Dunlap Observatory 74-inch telescope. We are going to go now quickly to our outreach coordinator, Quentin Wayrich, for questions about the DDO or the facility. Quentin, has anyone been asking questions?
Yeah, well, we have a question from AB who asks, do you ever put a camera or instrument or eyepiece at the focal plane of the DDO scope? And I guess we've got a CCD camera there right now, don't we?
Yeah, we do. So we are using, I believe it's a 20 megapixel CCD camera. It's on loan from one of our RASC members, Francois Van Heerden. Thank you so much, Francois, for the loan of your camera. And he's loaned it to us just so that we can bring you some of these live programs. Any other questions?
I do not believe so, no. Thank you.
Okay, thank you so much, Quentin. On behalf of the Royal Astronomical Society of Canada Toronto Centre and the RASC DDO Committee, I would like to thank Dr. Nassim Bozorgnia one more time for sharing this incredible glimpse into research around dark matter with us this evening. Thanks also to our technical support team, Andrew Reed and Betty Reed, and of course to Francois Van Heerden, who I just mentioned, for loaning us the camera that we have mounted to the big scope tonight. Thanks especially to Quentin Wayrich for fielding questions from our YouTube audience, and of course to Chris Vaughn for operating the big telescope tonight and bringing you that fantastic image of Regulus. Finally, of course, a special thank you to all of our viewers for joining us this evening and for your questions. This talk is part of our 2022 season of astronomy events at the David Dunlap Observatory online, offered through the partnership of the Royal Astronomical Society of Canada Toronto Centre and the City of Richmond Hill. We have a few upcoming events that you might want to stay tuned for. We have Ask an Astronomer. That's all. Tickets for that have already been sold on May 15th. So those folks will be joining Chris Vaughn to ask him some detailed questions about astronomy. There is another event, Ask an Astronomer event coming up on June 12th. So if you want to join Chris Vaughn then, please do sign up. We have an Up in the Sky event coming up on May 20th and then again on June 17th. In Up in the Sky, we show you live views of the night sky, weather permitting. And of course, if it's cloudy, we have lots of pre-recorded images. We'll give you all kinds of information about our solar system and the cosmos. We have speakers. Our next speakers night is on June 11th, so stay tuned for that. And of course, on June 19th, we have Sunday sun gazing. In this event, we offer you live views of the sun. So we have our specialized filters in place. We do safe solar observing, and we live stream those views from our RASC member telescopes. All of these events and more are posted on our website, rascto.ca. So please look there for more details. We're really hoping that tonight's event has you very excited about trying astronomy for yourself. So to cap off the evening, we have a short video for you with some tips about getting started in astronomy. Wishing you a wonderful night and clear spring skies.
A question we're often asked is, how do I get started in astronomy? It's a really great hobby, especially in this COVID context. It gets you outside for fresh air, you don't need to do it in a group, and there are tons of free resources online. So here's a quick guide to getting started in astronomy. Step 1 is to learn the sky. This really is essential, as it's important to be able to orient yourself and know what you're looking at. There are lots of resources to help you with this. If you prefer books, I can recommend Night Watch by Terence Dickinson or The Beginner's Observing Guide by Leo Enright. Or if you'd like to print out some star maps and star finders, There is the star finder from the Royal Astronomical Society of Canada. That's a printable star finder that you can take out with you under the night sky, or you can print sky maps and sky atlases from skymaps.com. If you're a little more tech savvy and you prefer programs and apps, I recommend Stellarium. This is free planetarium software you can install on your home computer, or Sky Safari. This is an excellent app for your phone. Once you've got your bearings, step 2 is to start observing. That's right, just head out under the night sky and look up. You don't need any special equipment, just your eyes. With your eyes, you can see things like constellations and asterisms. These are the formal and informal patterns that stars make in the night sky. You can see planets like Mars and several other planets as well. You can see the moon and observe its different phases as it moves across the sky. You can see meteor showers, comets, and even one galaxy that's bright enough to see with your naked eyes in a very dark sky area. Maybe you're inspired to look for more than what you can just see with your naked eyes. So step 3 is it's time to start collecting some gear. Now, you might be surprised that you may already have some of the things you need lying around the house. If you have a pair of binoculars, you can point those at the stars. If you don't, they're a small investment with a lot of benefits. With binoculars, you can see details like craters on the moon, or the phases of Venus and the moons of the planet Jupiter. You can even see smaller, fainter asterisms and double stars. Remember, one of our famous astronomers in history, Galileo, started out by using a telescope that didn't have much more magnifying power than an average pair of binoculars. His contributions to astronomy are remarkable, and you can see a lot through your binoculars too. If you're ready to get a little more serious about your astronomy hobby, you might consider investing in a telescope. A small amateur telescope is a big investment, but with more magnification possible, you can see more detail on the surface of planets, the moon's craters. You can see many double stars, some galaxies, and nebulas, and other deep sky objects. I recommend joining the Royal Astronomical Society of Canada to participate in the telescope loan program if you're interested in buying a telescope. You'll have an opportunity to try out many different scopes and determine which one is best for you. And this brings us to step 4, connect to a community. You can find information about the Royal Astronomical Society of Canada Toronto Centre online at rascto.ca. And through RASC, you can learn about upcoming astronomy events, you can find more astronomy resources, and you can become a member of the club for additional benefits, like that telescope loan program I mentioned. I hope this guide has helped you to feel confident in getting started in astronomy. Enjoy those clear night skies.